Okay, so this is the notion of the difference between the two models of light. Okay, and so for waves, it's really pretty simple. Okay, if you're dealing with color, wavelength changes, and I think you have this. Yes. Okay, so small wavelength is blue light, and large wavelength is red light. Large is red, small is blue. It's very simple. Okay, and if it's brightness, if we're talking about the brightness of a light, well, brightness is the amplitude. Okay, bright light is a large amplitude wave, and dim light is a small amplitude light. So this is dim, this is bright. Yeah? Okay, two different ways of expressing color and brightness, which are, can we stop? Thanks. Okay, so two different ways of expressing color and brightness. Yeah?
Now why is it the change instead of the amplitude?
Say it again.
Why is it the change instead of the amplitude? Because why the change in the amplitude?
Oh, to change brightness, you change the amplitude. That's what I mean.
Oh, okay.
That's why I'm saying that. Yeah, brightness is amplitude, right? With photons, okay, if you're talking about color, we're talking about energy per photon. And basically, by the way, if you want to talk about photons, photons are useful when the light is interacting with particular atoms. Okay, when we're looking at light as rays of light hitting water and refracting and stuff. We're going to use wave stuff, right? We've already done that last year. But when we do chemistry, right, that's all molecular interactions. And pretty much this is what we're going to do, right? So energy per photon changes, and so radio waves versus X-rays. Radio waves have a much lower frequency, therefore much lower energy, whereas X-rays, we're bathed in radio waves, and that's safe, isn't it? We don't really know for sure, but we think so, right? Okay. X-rays, though, the person leaves the room to give you the X-rays. Like, you stay there, I'm going to zap you with these harmful rays, right? Okay. And then brightness is just simply it's not the energy per photon, it's just the number of photons. A bright light like that laser, right? The wattage was the brightness of the laser. And all you had to do, you didn't change the energy per photon. Jordan, can we stop? Guys? We didn't change the energy per photon, we just changed the number of photons, yes? Okay. So brightness is the number of photons, many is bright, and fewer is dim. And this is, we would say fewer, not less photons, because we can count the photons. They're discrete things. Anytime you can count it, you have to say fewer. This is an irregular comparative in the English language, and we don't have that many. So it's good to know the ones that we have, right? Fewer people, less noise. Less sand, fewer grains of sand. English lesson in physics. See, I'm teaching to the literacy target. There we have it. Okay? Yeah. Fewer quantum jumps, less energy. Okay? There we have it. So these are two different models. Yeah.
You know those machines when you go through security at the airport?
The new ones?
Yeah, the new ones.
Yeah.
Like, the little diamond thing.
Yeah.
Those X-ray machines.
They are, I think they are, but they are just surface scanning, and so we think they're safe because the dosage is fairly small. The people that are critics of them say, look, it's all concentrated on the skin, and so it's not really safe because it's only penetrating the skin layer or something like that. And so, but I haven't really read up on them. But yeah, no, they're.
Guys that stand, like the security guards, they're standing there like all day.
Yeah, but it's not hitting them, it's going away from them. I don't know why it's safe. Yeah, I don't know. Okay, now, okay, let's fast forward because this is the exciting. Okay, shh, guys. I don't know the answer to that, but I do know this. Okay, so finally, Einstein, he proposed this, and by the way, nobody believed that light was these little particles called photons, right? Everybody thought that Planck's quantization would go away, and even when it didn't, nobody wanted to accept that light was particles. But Einstein said, look, here's a way that can prove it. He devised a way to measure the energy of light, specifically of photons, okay? And so the first thing you got to understand is that there's something called the photoelectric effect. When light shines on a metal, and this is well accepted, okay? If light shines on a metal, if it's got sufficient energy, it will actually eject electrons from that metal. It's got enough energy that it can send electrons flying from the metal. Okay, this is called the photoelectric effect, and in this circuit, they're actually using the photoelectric effect as like a light detector. Okay, so if you look at this, here's a battery. Electrons that are ejected from this spot here, this side is negative, this side's positive. What do? They accelerate across. As soon as they're liberated, they accelerate across, and they complete the circuit, and the fact that they're moving across is detected by the ammeter. And these are used as, until they had transistors that did the same thing for much cheaper and much more reliable, right? Okay, this is an evacuated glass tube, and those things are tricky, right? So until we got like transistors that did the same thing, this is how all light detectors worked. They used the little photoelectric cells. Okay, we still use them because they're very, very sensitive. We use them to detect other kinds of radiation in something called a photomultiplier tube. But anyway, that's the concept. Now, these two theories, and Einstein knew this, give different predictions. Okay, wave theory says, wave theory can predict the photoelectric effect, and wave theory says, look, what you want, it's the electric field. Okay, it's the electric field that is ripping the electrons off the metal. Yes, because electric fields are fields that exert force on charge. It is the electric field that rips the electrons off the metal, right? And so what matters with light, with the wave theory? What is the magnitude of the electric field? Is that the color or is that the brightness? That is the brightness, and for a wave theory, it is the brightness that matters. Should the color matter? Matters. There should be an R there. Should the color matter? No, the color is just how closely spaced they are. Yes? Okay. It is the brightness that matters because bright light means big electric field, which means it's that the electrons are going to fly off the surface with a greater speed. Okay. Color should not matter, but brightness should be the thing that matters. Now, let's look at photon theory. Photon theory also... No. They have mass but no charge. But they're pure energy, no rest mass, they're just pure energy, right? Now, okay, Einstein said, look, in my theory, what happens is the energy of the photons is expended and it's given to the electrons. And the energy depends on, what does it depend on? Depends on the frequency, depends on the color, okay? So with the photon theory, the color matters, the frequency matters, right? Does brightness matter? Well, brightness would just mean more photons, but not more energetic photons, right? Now, clearly these both can't be true. It can't be that brightness matters and color doesn't, and also at the same time that color is the only thing that matters and brightness does not, right? They cannot both be true, and Einstein knew this, right? If this is true, if color does matter, then Einstein's right, and wave theory in this case does not apply. Doesn't mean it's wrong, it just means it doesn't apply, right? Now, the problem is, here's the problem, is that the only, if you look at the periodic table, the only one of these guys that has electrons that are so up for grabs that you can knock them off with visible light, which isn't terribly energetic, are these guys right here, the sodium, potassium. These guys really, really want to give up electrons, yes? To become like the noble elements on the other side, don't they? Isn't that the deal with them, right? They want to become +1 ions, right? Give up the electron. And so the problem was that you had to do a thing with sodium metal, which oxidizes instantly, even in pretty good vacuums, right? There's enough oxygen in there to oxidize it. You have to do the experiment with sodium or cesium or something like that. It's very, very difficult. The person who ultimately did the experiment was Robert A. Millikan, the same guy that did that horrible experiment with the oil drops that we did, the simulation of, right? He actually did this. He made a little machine shop in a vacuum, and he had to slice the metal, so he had a clean piece of metal in the vacuum, shine light of a particular frequency. We had to use visible light at the time because that was the only light that we could isolate and separate and everything, right? And he actually showed that the photon theory was the only one supported, but still didn't believe it, right? It wasn't, anyway, it's an interesting story, right? Okay, now, here's what Einstein said, okay? And this is what you must understand. In fact, this is the first question on the test. It says, how do you, using this apparatus, determine the energy of the photoelectrons, the ejected electrons, okay? So what Einstein said is, look, take a photocell and reverse the voltage. Reverse the voltage so that you're not helping the electrons go across, you are preventing them. Now, does this mean that no electrons can get across if you make it so that they're heading toward a negatively charged thing? Well, doesn't it depend on the voltage? couldn't there be a sufficiently small voltage that the electrons could coast